Alrighty. Let's do this. So our next unit, okay, is going to be kind of like, feel like in a sense, when we start out at least, like taking a step backwards, okay? We're going to be going into, we're going to like review basic integration techniques, all right? So that means, kind of like going back to some of our, old tricks where we would have to like sometimes like, split up a numerator, or look for inverse trig, or yes. Oh, let me get you one then. All right. So, anyone else need a note? Okay. Any notes? So, we're going to review those basic integration techniques. We're not going to necessarily learn anything new today unless you haven't seen it in the past. No, that's okay. Okay. So, okay. And then from beyond today, this whole unit, okay, is going to be based off of learning some new techniques to kind of expand our, toolkit when it comes to attacking integrals and stuff like that. Integration by parts, okay. This will be, I think, like, we've already kind of touched on some BC topics, okay, but, we're going to, like, really dive into BC topics now. This is not an AB topic, okay, so your friends in AB won't be seeing integration by parts. Then we'll get into another technique called partial fractions, okay, and then we'll talk about indeterminate forms and L'Hopital's rule, and that's something that you can use in AB, but you don't necessarily get to. And then finally, we'll talk about improper integrals, okay? And so an improper integral involves taking the integral from a number like a to infinity, okay? So you can like integrate to infinity and stuff like that too. Kind of interesting. Yes, it is a person's name, yeah. Yeah, well, maybe he thinks our names are weird because, we're Mike or Mark or whatever kind of thing. So probably not. But I mean, if he did, he might. So anywho, all right, moving on here. So today, again, just review, nothing new. But again, if some of these are pretty tricky. Remember that integrals, right? The way, like one way I like to think about integrals, I think the book kind of describes in this way, right? The derivative, when you take the derivative of something, it's like, here's the problem, what's the answer kind of thing, right? Whereas with integrals, it's like, here's the answer, what was the problem that originally gave that, okay? It makes it a little bit trickier, all right? It's not as straightforward, okay? So we're going to look here at three closely related integrals, right? You'll notice here, they look very similar to one another. They all have x squared plus 9 in the denominator, and this first one here just has a 4. This one has a 4x, and this one has a 4x squared. And as we go about integrating these, we're going to end up with significantly different solutions, even though we start with something that looks, very similar to one another. They just all differ by, a power of x in their numerator there. Okay, so looking at the very first one there, what are we going to use here to integrate this? So, Cassie? So we could try u substitution. What would you want u to be here in this case? What's that? The denominator. Okay, so let's try that. Let's let u equal x squared plus 9. Okay, and I'll zoom in some here since we're just focusing on that one problem anyway. Okay, let's let u equal x squared plus 9. If that's the case, then our du will equal 2x dx. Right? Right, but that's good because this is the process you're going to be going through, right? Okay, this is what all you guys are going to be going through. You're going to try something. You're like, let's try this. It doesn't work, right? And as you kind of like struggle and choose something and make a mistake and then try something different, this is how you will get better at doing integrals, all right? There is no there are some guides we can kind of give you, but for some of this, it's going to be the struggle. That's all there is to it, okay? So, right, it's important to recognize then, right, we can't use this because there's no x in the numerator there for us to then get the x dx that we need. So, unfortunately, that's not the case. So, other ideas here, what could we use? So, all right, let's go, Caitlin. Arctangent, as I was going to say, Aubrey too. Yeah, arctangent is exactly right. All right, so what kind of clued you in here to the arctangent, Caitlin? Can you kind of...
The x squared plus 9.
Okay, right. We have x squared plus another perfect square of 9. Now, 9 doesn't have to be a perfect square. You know, this number here doesn't have to be a perfect square, but it's like an x squared plus a squared, so it's a good candidate for that, yes. Okay, so I'm going to pull the 4 out front here because it is a coefficient, right, and make it 1 over x squared plus 9 there, dx, okay. And so for the arctangent, remember we had to kind of like identify our u and an a here. So u would just be x, okay, because that's like the thing that's being squared there is the x. And then this is like a u substitution, so we would end up then with just dx. Okay, so the du would just be dx there, which is good. All right. And then what is our a in this problem? 3, right? Because 3 squared would give us 9, so a is just 3. Okay, and so if if you've forgotten your arctangent integral there, well, we're going to have the 4 in front still because that's our coefficient that was in front of the integral. And then arctangent, does that one have the 1 over a in front or not? It does, right? It does. Okay, so we're going to do 1 over 3 arctangent of x over 3 and then plus c, like that. Okay, which of the arc or inverse trig functions don't have the 1 over a in front of it? It's the arc sine. It's the arc sine does not have 1 over a in front of it. So the arcsecant will, arctangent will too. Okay. Really, again, if you like a hierarchy's sake, arctangent, you really ought to know that one. That one is like the most common one you'll see on the AP questions, AP tests, that kind of thing. Arc sine would be like the next most common, and then like way down here near the floor would be how often you see arcsecant. Not that you shouldn't know it, but like if you're gonna invest your time, really make sure you know arctangent. Then also make sure you know arc sine, and then arcsecant. I mean, you should know it, but it's the least common, I would say. All right, now let's go to letter B. And Cassie, what technique should we use here? U substitution. Very good. Okay, so now we're going to let u equal x squared plus 9. So du equals 2x dx. We've got 4x. I'm going to actually manipulate this a little bit here. I'm going to make this, all right, 4x squared plus 9 dx. I'll pull the 4 out front again and make it just x over x squared plus 9. Again, you do your u substitution slightly different from me. That's okay. Mr. Goff does show it, I think, in a bit of a different way, but that's, your choice. So I have an x dx now in my integral. I have 2x dx is equal to du, so I will move the 2 over, make it 1/2 du is x times dx. And so now since I have exactly x dx, I can replace that with this 1/2 du in my integral here and make it 4 times 1/2 the integral of du over u. Okay. So far, so good on that. Questions? All right. Because again, I know it's funky. If it's a little bit different than what Mr. Goff does there too. So just want to make sure we're okay. All right. What is the integral of du over u? Natural log of the absolute value of u. Yeah. So we'll go ahead and 4 times 1/2 is 2. Natural log of the absolute value of u. Don't forget the plus c. These are improper integrals. Indefinite. There you go. I put that word improper in my head from before. Yeah. These are indefinite integrals, right? And so you want to make sure you put that plus c in there. Okay. We've been doing a lot of work recently with definite integrals because we were doing the area, the volumes of solids, the cross sections and stuff like that. So you want to make sure you put that plus c. Don't forget. Okay. And then finally, we'll substitute in for our u, which is x squared plus 9 plus c. Okay. Is it necessary for us to have those absolute values in our natural log still? Why not? X squared is always going to be positive. Adding 9 further to that will still be positive, and so you can drop the absolute values if you really want to and just make it x squared plus 9 plus c. Okay? It won't ever be negative. All right, so far so good there. Okay. Moving on then to letter C. So now we got 4x squared over x squared plus 9. All right. So ideas here, what we would do. Yeah. Divide it. Exactly right, Sarah. Yes. Okay. Yes. Divide it. Okay. So long division, our favorite, right? So remember that we're dividing by x squared plus 9. So that's going to go on the outside. You don't need to do this, but I like to put a placeholder here, right? Since there's a missing x term, I'll put a plus 0x, and then we'll put the 4x squared, and again, I'll put some placeholders in here, plus 0x plus 0, okay? I just find putting those placeholders makes it a lot easier to do. Okay, so let's see if we can remember how to do long division. We need something times x squared to give us 4x squared. 4. Very good. 4 times x squared is 4x squared. 4 times a 0x is 0x still. 4 times 9 is 36. And we're going to subtract that quantity. Okay. But instead of subtraction, I like to make it add the opposites. Okay, you guys can get weird with negatives and stuff like that. So the 4's will cancel as they should, right? That's how we do long division. You need to make that lead term cancel. The 0's will still be 0, and then 0 plus negative 36 is negative 36. Okay. Can we multiply something by x squared to get negative 36? So this is our remainder, and so it's going to be minus 36 over x squared plus 9. That 36, right, we have yet to divide it. We have not yet divided it by the x squared plus 9, and so we're going to put it, still has to be divided there. This 4 we arrived at by dividing by the x squared plus 9, but the 36 still needs to be divided by x squared plus 9, so we put it in there. Minus 36 over x squared plus 9. Okay, so now we've got that. This is what we're going to integrate. Okay. And we can integrate 4x, we can integrate 4 easily using, our normal integration rules. To integrate this 36 over x squared plus 9, we're going to have to use arctangent again, our friend, arctangent. So we're going to break this integral up, make it integral of 4 dx minus, I'm going to pull the 36 out front of that integral 2, make it 1 over x squared plus 9 dx. Okay. So integral of 4 is 4x, right? Minus 36. And then if you'll permit me here, we already did the integral of 1 over x squared plus 9 right there. And so I'm just going to use what we got, right? The 1/3 arctan x over 3 plus c. And voila. There we go. You can simplify if you want, make it, 4x minus 12. But really, either of these is acceptable. Simplifying that solution, right, though, can be critical when it comes to like a multiple choice question. Right? Multiple choice, you need to be able to simplify your integrals and make your answer match what the multiple choice has. So that's part of that. You want to make sure you can simplify stuff. So do that. Okay. So little bottom piece here. I'm just going to highlight. All right. It is very important to know all the integration rules inside and out so you know which integrals apply to those particular rules, okay? Do not force a problem into a rule. It must fit perfectly, okay? So as an example of this, right, something that we can kind of like take for granted. If we see something like e to the 2x dx, right, we're like, oh, integrating e to the something, that's easy. It's just e to that something again, right? Plus c, and that's the answer. But that's not right? We don't know how to integrate e to the 2x. All we know is that the integral of e to the u is e to the u plus c. The problem is here we have a 2u, okay, or 2x. And so you really need to use a u substitution. So du equals 2 dx, right, or 1/2 du, I'm running out of space here, equals dx. Okay, and so this is really the integral of e to the u, or 1/2, the integral of e to the u du. So it's 1/2 e to the u plus c, or 1/2 e to the 2x plus c. Okay, so you really want to make sure those integral rules, right, those are like forms that we need to match before we can then integrate to use that rule, okay? So here, right, is what I'm trying to say. We can integrate e to the u. Trying to integrate e to the 2x, we do not know how to do. We have to change that using a u substitution to make it integral of e to the u, and then there's the 1/2 there, and then we know, aha, integral of e to the u is e to the u, okay? So just watch that kind of stuff. All right, that's what we're trying to emphasize here. All righty, so moving on here. All right, number 2. So for situations like this, all right, we want to evaluate now it's a definite integral from 0 to 1, x plus 3 over the quantity 4 minus x squared. Okay. So I'll just go ahead and say we're going to break this up. Okay. Make the numerator break that up over the denominator. So we'll make it integral from 0 to 1 of x over quantity 4 minus x squared dx plus then the integral from 0 to 1 of 3, and I'm going to pull that 3 out front if you'll permit me there, make it 1 over the square root of 4 minus x squared dx. Okay, sorry, off the screen. There we go. Okay. And again, sometimes you'll see something that's kind of messy like this, and you'll be able to do it all at once, right? For example, maybe we could have used a u substitution here. Maybe we could have said let u equal 4 minus x squared, but then if we let u be 4 minus x squared, our du would just be negative 2x, and we don't have, we have negative 2, we have an x plus 3, and to make that match negative 2x, it just wouldn't quite work, right? But breaking this up, now we can see what we can do here, okay? For this one, what are we going to use to kind of go to proceed from here? We need to do what? U sub, let u equal what? 4 minus the x squared, exactly right, because then we'll have the du be negative 2x, and we can make that match the x dx, no problem. And then, are we going to use a u substitution here? No, this is a arc sine, right? This is what Mr. Wood was just warning us about, right? Arctangent and arc sine, those are the two big ones we need to know. All right, so first one here, let's go ahead and do that. So we'll let u, and this is where I can got, because we got so much going on, it'd be kind of hard to like organize our work and make it look, you know, halfway decent. So I'm going to do the u substitution above here, and so I'm going to say let u equal 4 minus x squared. So then du will equal negative 2x dx. We just have an x dx, so I'll move that negative 2 over, make it negative 1/2 du equals x dx. And so then this becomes the integral from, and I'm not going to bother changing my limits of integration here, I don't think. Yeah, I'm just going to leave them. So I'll put the 1/2 in front, though, and make it, well, this is 1 over the square root of u du, okay, plus 3, okay, and then let's just go ahead and continue on with this one, right? Rather than maybe trying to, maybe breaking our train of thought and going on to try now do this one and then do these like two things simultaneously, let's just continue with this one, okay, this flow here. And so instead of 1 over the square root of u, let's, oh, did I make a mistake?
Negative 1/2.
Thank you, it is negative 1/2. Thank you, okay, very good. Okay, so negative 1/2. But instead of 1 over the square root of u, let's make that instead u to the what? U to the negative 1/2 du. Yeah, okay. Much easier to integrate that way, right? And so then that'll give us negative 1/2. And then that will add 1 there, so it becomes u to the 1/2, but then it times a 2, or times 1 over 1/2 kind of thing. Okay. And then I'll go ahead and substitute in the negative 1/2 times, what was our u there? Oh, I guess I'll make the negative 1. Negative 1/2 times 2 will be negative 4 minus x squared to the 1/2. There we go. Almost off the screen. There we go. Okay. So there's that first piece, right? We got right down there. And now we'll work on this second piece, right here, the second part. And so, well, I guess I don't really need to do an integral here. I can just continue on. Yeah, bless you. So since this is going to be arc sine, again, we need to identify a u and an a here. So our u is what? Just x, okay? And our a is 2, okay, right? 2 squared gives us the 4, so u is x, and yes, a is 2.
What happens to the minus? Like, would it be negative x? Is it u? Or is it just x?
Oh, so the arc sine's format is root a squared minus u squared. So the minus is supposed to be there as part of the form, yeah. okay? Which compare that to arcsecant, which is absolute value of the square root of u squared minus a squared. So arcsecant, like the x squared would be in the front of the square root and also, well, in the front of the square root and also at the, it's the beginning of the difference there. But for arcsine, it's a squared minus u squared. So that's what the format we want, okay? So anyway, I think we're ready to integrate this then here. So the integral of 1 over 4 minus x squared. So again, we said arcsine does not have the 1 over a in front of it. So it'll just be the 3 there times the arcsine of, and then what's going to go inside the arcsine though? X over 2. Yeah, u over a, x over 2. Yep, exactly right. All right. And I'm going to keep bringing that down here until I get down to this final step here where we had it all back in terms of x, and now I'll evaluate from 0 to 1. Okay, is there a more elegant way to write that? Probably. Okay, probably. I'm not doing it though. All right. So now we'll plug in our numbers, right? We'll plug in 1. All right, and so we'll say negative, and then we'll plug in the 1 here. So 4 minus 1 is just going to be 3, so it's going to be 3 to the 1/2. Okay, plus, and then we'll have 3 arcsine of 1/2. Okay, so that's like our upper bound plugged in, minus, and now we'll plug in 0. So it'll be negative, let's see, 4 minus 0 is 4 to the 1/2. Plus arcsine of 0, 3 arcsine of 0 over 2, which is just 0 there, of course. And if this is a free response question, we're done, right? We're done if this is a free response question. But we don't know that, so let's kind of keep going here with this, right? So this is then negative square root of 3 plus 3 times the, oh man, we got to remember how to evaluate inverse trig. Well, let's go back here now, right? If arcsine, if we're trying to evaluate arcsine of 1/2, okay, our answer is going to be some angle, right? So we want that it's going to equal some angle theta, right? For inverse trig, you plug in a ratio, you get out an angle, right? For regular trig, you plug in an angle, you get out a ratio, right? But it's reversed for the inverse trig. So, or we can also think here, 1/2 is equal to the sine of what angle? And so it's going to be what? Sine of what? And it's going to be, first quadrant since we're positive here. Sine of what gives us 1/2? Pi over 6. Okay, pi over 6. So it's 3 times pi over 6. Okay, minus, and then 4 to the 1/2. That's easy. It's going to be 2. So it's going to be a negative 2 there. Plus, and then 3 times, and then arcsine of 0. Or in other words, sine of what gives us 0? 0. Okay, so it'll just be times 0 there. Okay, so that'll just be 0, and we're subtracting a negative 2, so it becomes plus positive 2. So then the 2, it'll be negative root 3 plus pi over 2 plus 2. And that's our final answer there. Okay. That's pretty intense, yeah? It's pretty intense. But this is, kind of like how difficult it can be. And this is stuff that we, know how to do, right? But that's a lot of stuff going on there, a lot of opportunities for mistakes. I mean, heck, I even forgot to put the negative there in front of my 1/2, right? So be careful there. Be careful. All right? Any questions on any of that? All right. So let's go on here to number 3 then. And why don't you guys give this one a try? I think you're up for it here, right? Okay, so why don't you try number 3 there? All right, at least set it up, right? At least set it up. Okay? So I'll give you like 30 seconds or so to at least set it up. And then maybe even at least ponder how you might integrate from there. So at least hopefully there's our setup, right? 0 to k, integral of 0 to k of e to the x over 1 plus e to the x dx equals the natural log of 3. Okay. What would be our technique here that we would want to use in order to integrate this? U sub, let u equal 1 plus e to the x. Okay, du equals e to the x dx. Okay. And so then when we integrate, that's exactly what we've got, right? E to the x and the dx there. So this is just really 1 over u du, all right? And that's, again, still equal to the natural log of 3. All right. You can change your limits of integration here. It's really up to you, whether you want to do that or not. I think I'm going to not change them this time, just because just on a whim, all right? So then the integral of 1 over u is the natural log of the absolute value of u, okay? And that's, again, equal to the natural log of 3. And then we'll put in our 1 plus e to the x, and we'll evaluate that from 0 to k. Okay. Again, do we need the absolute values here around 1 plus e to the k? Oh, question?
Can we go over how you did that in the higher thing yet?
Yes. So are you okay with the u substitution?
I'm okay with the use of
Okay, so we got 1 over u.
Okay.
The integral of 1 over u, right? Natural log of the absolute value of u.
Okay.
Right? And then I substitute back in the u, but back in terms of x, so that I could use then my old x limits of integration. I did not. So what I've done in the past is I've changed my limits of integration to be in terms of u, and then evaluate from the u, not from the back in terms of x. I just did it this way just to change it up, just because some people do it differently, you know. So at this point, right, back to my original question: do we need to have the absolute values around 1 plus e to the x? No, right? E is like 2 point something. 2 in x power is still going to be positive, no matter whether it's negative or positive power. Plus a 1 is still positive, so we can drop those, but anywho. So this is then 1 plus e to the k, okay, minus the natural log of 1 plus e to the 0. Okay. Be very careful, right? Because like a lot of the times when we have 0 as a lower limit, right, that means the lower limit kind of goes away. It equals 0. Does that happen in this case? No. What does this simplify to be? Natural log of 2, right? Because e to the 0 is 1. 1 plus 1 is 2. So be very careful there, okay? I know we can get in that habit, and sometimes I'll do it too, but we got to be very careful. It is the natural log of 2, and that equals the natural log of 3 there. Okay. So how should we go about trying to simplify this? What should we do? Yeah. Move natural log of 2 over by adding to both sides, right? Okay. And when I add these, we'll have ln3 plus ln2 natural log 2. But since we're adding two natural logs, we can combine that together as a single logarithm. It'll be equal to the natural log of... Ooh, right. Is it 5 or 6? 6. When we add two logarithms, we multiply, okay, inside. So this is equal to 3 times 2, so it's natural log of 6. Okay? And now since we have a natural log on this side and a natural log on this side, right? I'm going to actually rewrite it here just because I like to push it to the limit here. There we go. All right. Now what should we do from here? E both sides, right? E to the power of each side. So we have 1 plus e to the k equals 6. E to the k equals 5. K equals natural log 5. Okay. Yes. Question, Mike?
Instead of adding the natural log of 2 to the other side,
Uh-huh.
can we do the natural log of 1 plus e to the k divided by 2?
Absolutely. Right. So alternatively here, right, since we have subtraction between these two logarithms, we can make it 1 plus e to the k all over 2, and then you'll have a single natural log, and solve it from there. Yep. Absolutely. Okay. Good on that? Moving on. All right. So number 4 then, the rate. Because remember, we also have like different ways we can apply the integral here, right? Before, just now, right, we were talking about the area under the graph, right? That's an integral. We didn't say integral, but we know that that's conceptually we need to use an integral there. Number 4, we're given a rate in which snow is falling, okay? R of t equals this for t greater than or equal to 0. How much snow has fallen on the ground from 0 less than or equal to t less than or equal to 4? So when we're given a rate and we want to find a quantity, right? That's another example of us using the integration, right? So we're going to integrate from what to what? 0 to pi over 4. Okay, when you integrate a rate, you get the net change, right? The net change. And so then we'll have cosine squared of t plus sine of t over cosine t. Everyone's favorite trig functions. Okay, there's our setup. Okay. Do we want to use a u substitution here? Yeah, maybe not right off the bat, right? Because if we let u be cosine of t, our du would be negative sine. We do have a sine, but then we also have this plus cosine squared. So ideas here about what maybe what we can do? So, yeah, Kurt? Separate the numerator, yeah? Exactly right. Okay? So, integral from 0 to pi over 4. Let's try that. So we'll have cosine squared t over cosine t. And again, if I'm writing too many steps for you, feel free to skip more steps than this if you like. But okay, so cosine squared over cosine is just cosine. That's nice. And then, we still have that sine over cosine, but that's just what? Tangent. Okay. Can we integrate cosine? We know how to integrate cosine, right? Can we integrate tangent? Yeah, we do have a rule for that. Whether you remember or not may be a different story, but we do have a rule for that, okay? So anyway, integrating cosine is sine, okay, t, okay? And then integral of tangent, so it's going to be negative natural log of the absolute value of cosine of t, okay? Negative natural log of the absolute value of the cosine of t there. Okay. Remember, the way we get tangent, and I don't know if this is going to be helpful or not, the way we actually integrate tangent is because if you remember how we did that back in the past, the way we integrated tangent was we rewrote tangent as sine over cosine. Okay? And to integrate that, then we use a u substitution. We let u equal cosine of x. Du then would be negative sine x dx. And so we ended up with the integral of negative 1 over u du there. And so there's where that natural log comes from, if you remember that. You know, like many weeks / months ago. I mean, I know it was last year, you know, kind of thing. But there it is, okay? And then we're going to evaluate that from 0 to pi over 4. Okay. But this can be a helpful way to actually remember how to integrate tangent. If you remember how we integrated it in the first place, that can help you remember what the integral rule is and stuff. Maybe. That's how I remembered it. So then again, I'm a math teacher, so. All right, so we'll plug in pi over 4, sine of pi over 4, root 2 over 2, minus natural log of the absolute value. Cosine pi over 4 is also root 2 over 2, but it's natural log of root 2 over 2. Okay. And that's our upper limit plugged in, minus sine of 0 is 0, minus natural log of the absolute value of cosine of 0, which is 1. So we end up with root 2 over 2 here, minus, natural log of root 2 over 2. Okay. And then, well, that's it, right? Because natural log of 1, 0, 0 minus 0, 0 minus 0, so it's just going to be that. Any of that? Still good? Still hanging in there? Okay. Number 5. Particle motion. All right. A particle moves along the x-axis such that its velocity can be modeled by the function v equals t times 1 plus 1 over t quantity squared for t greater than 0. Okay, so this is a velocity, okay, for t greater than 0. Rate of change of the position. Find the position of the particle at time t equals 3, given that the position at time 1 is 4. Okay, so we want to find the position x of 3. Okay, so I'm going to integrate from what to what here? I see what you're saying. You want to integrate without bounds, and we could. Okay, yes, we could do that. That's true. Let me think here. But we would have this point. So we could do that. We could integrate indefinitely here and do it that way. So one option is to find x sub t by integrating t times 1 plus 1 over t squared dt, okay, and then use 1 comma 4 to solve for c plug in t equals 3. Okay, so that's one option. I'm not going to do it that way though. I'm going to do it the other way, right? I'm going to do it with a definite integral. So if we just integrate from 1 to 3, our velocity here, and sorry, I know I'm blocking the thing I just wrote. That's really frustrating, I know, as a student, but okay, there it's away. Okay. So if we just integrate, is that going to give us the answer from 1 to 3? No. That would give us the net change in position, but we need to have like a starting place, right? This will tell us how much our position has changed from time 1 to time 3. Okay, but it's not going to tell us our location. It just tells us how much we've changed. What else do I need to put in here? 4 plus, right? We're starting at 4 at time t equals 1. And then if I integrate from 1 to 3, that will add the change from that position 4 to whatever the new position would be at time t equals 3. Okay, so I'm going to do it this way. This is not wrong. This is not wrong. Okay, but I'm going to do it this way. The one sticky part that you can get into with this method right here, this first method that we talked about, the one sticky part you can get into is like if this were calculator active, right, then you could get something that you can't integrate by hand, right? If you can't integrate by hand, this method kind of falls apart because our calculators can't symbolically, or I think symbolically integrate is what you would call them, or indefinitely integrate, I guess there, right? But if we do have our calculators, right, or if we do have our calculators, you can use this method, right? You don't need to know what the actual interval is. The calculator can still give you a value, just not what the interval actually would be. So you want to be comfortable with both ways here, right? Because you can get situations where you would need to use this one as opposed to this one. Okay. Anywho, let's proceed on here. So how should we proceed to integrate this thing? Ideas here. Square it out. Multiply it out. All right, let's try that. So I'll do this. All right, I'll do it over here on the side. 1 plus 1 over t times 1 plus 1 over t. Okay, so FOIL right. Oops, I'm off the screen. 1 times 1, that's going to give us the 1 there. Okay, we'll have a 1 over t, and then plus another 1 over t. So now we have 2 over t, exactly right, yeah. Okay. Plus 1 over t times 1 over t now. 1 over t squared. Okay, dt. Okay, that's looking better. That's looking better. Sean, what should we do then next maybe?
Put the t on the outside.
Can't pull the t out. T is a variable. It's not a coefficient. We distribute the t. Yeah, distribute the t. There you go. We're going to multiply that t through there. Okay, exactly right. Man, that makes it look much nicer. So t times 1 is just t. T times 2 over t is a 2. And then we end up with 1 over t dt. Okay. Oops, and I forgot to put a plus there. There we go. Woo. Okay. So now we can integrate this by hand, right? So let's see here. Integral of t will be 1/2 t squared plus 2t plus the natural log of the absolute value of t. And we're going to evaluate this from 1 to 3. So we'll have, let's see here, 9/2 plus 6 plus the natural log of 3 minus 1/2 plus 2 plus, well, the natural log of 1, which is going to be 0 there, but oh well, I'll write it anyway. Okay, so let's see here. It's going to be 4 plus 6, 10. Minus 2, though, will be 8. But then we're going to have 8/2, 4, so 12. Did I? 4, 6, 10, 12. and then, no, 8. Oh, minus 2, 8, and then plus 4. Yeah, 12. It was 12. Okay, pretty sure it is there. And then plus the natural log of 3. I do believe. Okay, I think I did that right. All right. No hands in the air, so certainly you just are taking my word for it this time. All right. Questions on that? All right. So on the last page here, we've got kind of a summary of different tips and tricks, okay, to use in your mathematical adventures in calculus, right? Because you're not going to have Mr. Widmeyer standing over your shoulder telling you, don't use that tip, don't use that way, kind of thing. You'll have to figure it out yourself. And that means some struggle, right? And so you'll have to practice your perseverance and things. All right, so the first one here, 1 plus e to the x quantity squared. The strategy here, multiply it out. Okay, 1 plus e to the x times 1 plus e to the x, right? Which would yield then 1 plus 2e to the x plus e to the x squared, which is really just e to the 2x. And then you need to use a u substitution for that one, but then these two you integrate, no problemo. Okay. In this scenario, we would want to break it up, split up the numerator. Okay, not the denominator. Okay, right, a plus b over c plus d, that does equal a over c plus d plus b over c plus d. It does not equal a plus b over c plus a plus b over d. Okay. You can break up a numerator over denominator. You may not break up a denominator. Okay. Okay. If you broke this up, right, you would have an arc. Well, I guess I'll go ahead and just write it 1 over x squared plus 1, which would be an arctan, right? And then x over x squared plus 1, which the technique here would be a u sub. Okay. How about this next one? The bottom, it won't factor, unfortunately, but that's a good thinking. Yes, it factor it. What's that? Negative powers, like rewrite it as like something to the -1. Okay, possibly, but then we would still need to use a u substitution there. All right, this one, you guys, you're not going to like it when I say it, but I'm going to say it anyway. Complete the square. Yeah, right. We did. I know that was like one question on one day when we were doing inverse trig, the arctangent stuff. But these kind of problems, right? This believe it or not, this is an arctangent problem. Okay, we'll rewrite it as I'll put them in order from from greatest to least power there. Okay, so do we remember how to complete the square? Okay, so this thing, right? This polynomial in the bottom, this quadratic, it is not a perfect square because we can't get it to break down into two things that will multiply by themselves, right? To give you then the x squared plus 2x plus 5, right? We can't factor this to two things that are the same thing. It may factor to two different things. I don't think this factors actually at all. So we have to make it. We're going to make it a perfect square. Okay. The way we do that, well, let me just kind of. So we have x squared. I'll do this over here on the side. We have x squared plus 2x. Can't see it. There we go. Okay. We have x squared plus 2x plus 5. If we want this thing to factor to be a perfect square, well, we need an x and an x, right? And then these two numbers have to add to make what? Ooh, they have to add to make 2. All right, and so we also need these two numbers to be the same. So they have to add to make 2, and they need to be the same. So what numbers do they have to be? 1 and 1, right? But the problem is, if we say this factor is to be x plus 1 times x plus 1, well, then the 1s don't multiply to make 5, they multiply to make 1. Right? So here's what we're going to do. We take the x squared plus 2x, and we're going to put in a plus 1 there like we want it to be. Okay? But then because we brought in, one second, Sean. So because we brought in a plus 1, we have to balance that out, right? Because we can't just add a number in and say it's the same thing. So I'm also going to simultaneously, I'll put in a minus 1, and then I'll also still have the plus 5 there as well. Okay? And so now I can factor this thing. It'll be x plus 1 times x plus 1. And then the minus 1 and the plus 5 simplify to plus 4. And so then we can see that's how we create that perfect square. Okay, so Sean, do you have a question?
Why do they have to be the same?
Because we want to make a perfect square. And in order for something to be a perfect square, it's got to be the same, the something times the same thing, right? So if that's going to be x plus 1, that also has to be x plus 1. If it's going to be a perfect square that we're making.
Okay.
We're completing a square, we're making a perfect square. So anywho, so that means this thing over here, right, if I could just take this, okay, put it in place here, we're going to have x plus 1 quantity squared plus 4. Okay, using all this work that we just kind of did right there. Okay, and now you can see the arctangent, right? There's our u, x plus 1. Our a is 2, and then the 3 we can pull out front as a coefficient. Okay, so this is arctangent. Can't wait to see one of those, right?
Yeah.
Quiz or a test. Very exciting. All right. So there's that. All right, how about the next one here? Oh, sorry, question, Kara.
Really fast. So for like the last part of that, when we had the 3 over the 1 plus x squared plus 4, would you separate that and then the one part would be arctan, or like what would happen?
No, so this whole thing, remember, we can't break up our denominator, so this whole thing would be arctangent. So you want me like, I'll show you the rest of it here real quick. So u would be x plus 1, okay? And then a would be 2. And are you good from there then?
Yeah.
Okay, so yeah, so it'd be 1/2, well, it'd be 3 times 1/2 arctangent x plus 1 all over 2 kind of thing. Okay, so I guess I'll just go ahead and finish that. 3/2 arctangent x plus 1 all over 2 plus c is what that would end up being right there. Okay, anywho, sorry. Next one, what's our strategy here? Long division, okay? I'm not gonna like go through that. Okay, just long division, exactly right. Dot, 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 all right? And then for our final one, with my smudged example there, all right, cotangent squared.
Know your rules?
Well, so cotangent squared, we actually don't have a rule for that. Well, so what would you want your u to be there? Cotangent? If we let u be cotangent, then the du, well, we wouldn't have it, right? Because the derivative of cotangent is negative cosecant squared. We don't have a cosecant squared.
Make it cosine over sine.
We could make a cosine over sine, potentially, and then do a u substitution. Let me see here. I don't know. I want to see now. Cosine squared x over sine squared.
What can I say? Okay, I have no idea.
I think our problem here would be that if we let u be sine, our du would be just cosine. We have cosine squared, so it wouldn't be quite enough. And if we let u be sine squared of x, then we would have 2 sine x cosine x, and again, it wouldn't be quite enough there. So not quite, but you might, maybe you could, I don't know if you could break up. No, I'm not sure. Maybe there's something to that, but what did you want to say, Sarah? Yeah, we're going to use a trig, Pythagorean identity here. Okay, so cotangent squared of x. Okay, well, we have the identity 1 plus cotangent squared of x is equal to cosecant squared of x. Which means that cotangent squared is equal to 1 minus. Sorry, cosecant squared x minus 1. Yeah, there we go. Should we do subtraction right, Mr. Witt? So there it is. Okay, now, can we integrate cosecant squared? Yeah, we can, okay? We can integrate cosecant squared. That's going to be a cotangent, well, negative cotangent. And then integrating the 1, we can integrate that too. It'll just be x. Okay, so we can integrate this. So Pythagorean theorem, or Pythagorean / trig identities will also be something that you want to use there. Okay, so we're going to rewrite that to be that. All right. Question, Sean.
How far back did you win the Pythagorean identities?
How far back?
Like, which-
That was like first week probably is when we went over those. Yeah, and also pre-calculus too, of course. But yeah, we reviewed them in there, and we haven't seen them very often. Okay, questions? We're good? Okay, so that's it then for today. Your assignment will be on the Google Classroom there if you want to get started, okay?